Today, we're diving into something that feels like it's been ripped straight from a science fiction movie, but it has some very real science behind it. We're talking about whole brain emulation.
So let's just get right to the heart of it. The big, wild question. Could you actually upload your mind, your consciousness, everything that makes you you, into a computer, and basically live forever?
I know, it sounds pretty out there, right? But what's fascinating is that back in 2008, a group of researchers at Oxford published a super detailed, honest-to-goodness engineering roadmap on how we might actually pull this off. And that's what we're going to unpack today.
So what is this thing really? Well, the official term for it is whole brain emulation, or WBE. And the key idea here is creating a perfect, one-to-one functional copy of a human brain in software. We're not talking about creating a generic artificial brain, we're talking about copying a specific brain, like yours.
Okay, this is a really important point to get our heads around. The word here is emulation, not simulation. See, a simulation just copies the results. A weather forecast, for instance, predicts rain, but it doesn't actually create clouds and pressure systems. An emulation is way more ambitious. It's like rebuilding the entire weather system piece by piece so that rain happens on its own, naturally, just like it does in the real world. That's the goal here. Now, here's where it gets kind of weird and counterintuitive. You'd think that to copy a brain, you'd first have to understand everything about how consciousness or memory works, right? Nope. The whole idea behind WBE is different. It's all about getting the details, the low-level structure, perfectly right. The bet is that if you can copy every last neuron and synapse with enough detail, then all the high-level stuff, thoughts, personality, memories will just emerge. So how on earth would you even begin to do something this massive? Well, that Oxford paper lays it all out. They broke down this absolutely monumental task into a 3-step plan. And here they are. It boils down to this. First, you scan the brain to make an insanely detailed 3D map. Second, you translate that map into a working software model. And third, you simulate that model, meaning you run it on some incredibly powerful computers. Simple in concept, mind-boggling in practice. All right, let's look at step 1, scanning. And this isn't just a drawing on a whiteboard. This is real hardware. This machine basically takes a preserved brain and shaves it into tissue slices so thin you can't even imagine. We're talking thinner than a wavelength of light. These slices are then collected on a continuous tape to be scanned by an electron microscope. And yeah, there's no getting around it. This process completely destroys the original brain. So once you have these mountains of image data, literally petabytes of it, you get to the translation step. And this is just a monster of a data problem. You have to write software that can clean up all those images, trace out every single one of the billions of neurons, pinpoint every connection, figure out what type of cell each one is. It's a data crunching challenge on a scale that's hard to even comprehend. And finally, you have to run the thing. So how does a computer pretend to be a neuron? Well, you model it like a little electronic circuit. Each part of the neuron is represented by things like resistors and capacitors. You build this giant virtual circuit board with billions of these little neuron circuits, and then you just let the supercomputer go to town, calculating all the electrical flow through this massive network. Okay, so scanning, translation, simulation. The plan is there. But now, it's time for a pretty serious reality check. Let's talk about the sheer, insane scale of the thing we're actually trying to copy. You see, the brain isn't just a bag of neurons. It's like a set of Russian nesting dolls. You've got these huge systems, which contain smaller networks, which are made of neurons, which have synapses, which rely on individual molecules to work. And the huge question is, which level of detail do you actually need to capture to get the person? Do we need to copy every single molecule? Nobody knows for sure. So let's just throw some numbers out here to feel the scale. First up, neurons. Your brain has about 100 billion of them. For perspective, that's more than 12 times the number of people alive on planet Earth today. But wait, it gets crazier. Each of those 100 billion neurons connects to thousands of others. When you add up all those connections, those synapses, you get to a number around 100 trillion. The web of connections in there is just staggering. So what kind of computer could possibly run a model this complex? The original paper estimated we need at least an exaflop machine. That is a 1 with 18 zeros after it. A billion calculations every single second. Back in 2008, that was pure fantasy. Today, well, we actually have a few of these, but they are gigantic nation-state level projects.
So let's do a little thought experiment. Let's just say we figure it all out. We build the perfect scanner, we write the perfect software, we have the giant supercomputer ready to go. We flip the switch. What have we actually made? See, success here isn't just one thing. There are levels to this. At the most basic level, a functional emulation, you might just get some electrical activity that looks like a brain in a deep sleep. But as you climb the ladder, you get to individual emulation, where it actually has the original person's memories and skills. And then you hit the really deep philosophical questions with mind emulation and personal identity. Is it conscious? Does it feel things? Is it actually the same person? And that really is the ultimate question, isn't it? The one that this whole endeavor forces us to look at. If we created a perfect digital copy of your brain, one that remembers your first day of school, loves your family, and has all your hopes and fears, would that digital being running on a computer in a server room somewhere actually be you? Or would it just be a perfect echo?